Acids and bases, high level 1. Lewis acids and bases. The essential idea. Many reactions involve the transfer of a proton from an acid to a base, and the acid-base concept can be extended to reactions that do not involve proton transfer. Nature of science. Falsification of theories. Hydrogen cyanide altering the theory that oxygen was the element which gave a compound its acidic properties allowed for other acid-base theories to develop. Theories being superseded. One early theory of acidity derived from the sensation of a sour taste, but this has been proven false. Public understanding of science. Outside the arena of chemistry, decisions are sometimes referred to as acid tests or litmus tests. Theories can be supported, falsified, or replaced by new theories. Acid-base theories can be extended to a wilder field of applications by considering lone pairs of electrons. Lewis theory doesn't falsify Bronsted-Lowry, but extends it. Lewis acids and bases. It's based on the transfer of an electron pair between reactants. So here you can see ammonia, and there's its lone pair, and it donates the lone pair to form a bond. You can see that this lone pair is being donated and it's forming this bond. So the ammonia has a dative or coordinate covalent bond to the proton to make NH4+. Because ammonia is donating the lone pair, is the Lewis base. So the Lewis base is an electron pair donor. And here the proton is a Lewis acid because the Lewis acid is an electron pair acceptor. So a Lewis base must have a lone electron pair. And a Lewis acid must have an empty orbital in the valence shell to accept the electron pair. Do note here that the ammonia is acting both as a Bronsted-Lowry and a Lewis base. Let's show how the reaction between ammonia and boron trifluoride is an example of Lewis acid-base reaction. Well, we've got ammonia here with its lone pair. We've got the boron trifluoride here, and as you know, boron is an exception to the octet rule, so it has some spare room for electrons in its valence shell. The ammonia donates the electrons to form a coordinate bond. So the ammonia is a Lewis base or electron pair donor, and the boron trifluoride is a Lewis acid electron pair acceptor, and we get this coordinate dative bond forming. Let's now show how the formation of complex copper-2 tetrahydride ion is an example of a Lewis base reaction. Water, each molecule of water has two lone pairs. One of these lone pairs is donated to the copper, which has plenty of spare room in its valence shell, and it can form 4 coordinate bonds. So the water is acting as a Lewis base as it's donating an electron pair, and the Lewis acid is the acceptor, copper being the Lewis acid. You can see the 4 dative bonds. Remember, you draw little arrows for dative bonds. In nucleophilic substitution reactions, both 1 and 2, the nucleophile is acting as a Lewis base. And remember, a nucleophile, or nucleus-loving thing, is an electron-rich species, neutral or negative charge, which is attracted to a region of electron deficiency. Here, the hydroxide ion, as can be seen, we could have used a cyanide ion or water or ammonia, but the hydroxide ion is donating its lone pair to that carbon, and the electron pair from that bond will move on to the chlorine, making a chloride ion. The hydroxide ion is acting as the Lewis base. It has a lone electron pair it is using to bond to the carbon atom. In electrophilic addition reactions, the electrophile is acting as a Lewis acid. Remember, an electrophile is an electron deficient species that accepts a lone electron pair from another reactant to form a new covalent bond in a reaction. So you've got, for example, boron trifluoride, copper ion there, hydrogen bromide, and the nitrogen dioxide ion there. So we've got bromine is more electronegative than hydrogen. Therefore, the electrons shift towards bromine, and away from hydrogen, forming a positive dipole on the hydrogen that is attracted to the region of high electron density on this pi bond. So HBr is acting as a Lewis acid, or more specifically, the H plus is formed as a result of the heteroelectric fission of hydrogen bromide is acting as a Lewis acid. Here's another example. That's more of a question than an example. How is the NH2 minus acting as a Lewis base here? Well, you can see it's acting as a Lewis base because it is donating a pair of electrons. And the C2H2 is acting as a Lewis acid because it is accepting a pair of electrons. I'd like you to press pause, go back through this and your previous notes and complete this table. Okay, you should also complete this diagram. Press pause and fill that one in. Okay, here you should have got something like, for the inside one, it would be a Bronsted-Lowry. And we know that Bronsted-Lowry is basically an electron pair going to an H plus. You must have this H plus. Whereas the Lewis ones would be a base electron pair going to any Lewis acid. Does not need to be the H plus. Acid base theories. Press pause. Have a go at these questions. Okay, it asks you to describe the acid-base behavior of aluminium and chlorine atoms. You can see straight away chlorine is donating lone pairs, so it is the acid. Aluminium is accepting lone pairs. Oh my, that's the wrong way around. Chlorine is donating lone pairs, so it is the base. Aluminium is the acid as it's accepting the lone pairs. Which reactions are Lewis acid-base reactions? Well, you've got, this will be in solution, so you've got say magnesium 2 plus here, and you have Cl minus with its lone pairs. Cl minus will be donating lone pairs there, so that is. Here, hydrogen oxygen to give water. This is a series of homolytic fissions and sort of stepwise reactions, so this one wouldn't be considered it. Here you've got copper 2 plus and 4Cl minus making this complex. Obviously, the copper has plenty of spare room in its valence shell to accept lone pairs from the chloride ion, so this is going to be Lewis acid-base reaction. And here you've got sodium hydroxide. You're going to have a nucleophile here, the OH minus, which is going to be using its lone pair to attack the carbon, and then you're going to get heterolytic fission here. So this would be considered a Lewis acid-base reaction. And that's the end of that. Splendid.